Let's move on to one more model. This is an epidemiological model, particularly relevant given the current situation that we've all been going through for the past 5 months or 6 months or so. And this is actually exactly the kind of model that you might be seeing presented, that numbers are being presented from in the news with regard to COVID. Imagine that you have a contagious disease pass between people. On any given day, some people will get infected. Some people who were infected will recover. We're going to assume that for this particular disease we're dealing with, after someone recovers, they become immune, similar to chickenpox, similar to measles, hopefully similar to COVID-19, although we're unsure of that. And the model that we're going to be developing is going to be thinking about the number of newly infected people being directly proportional both to the number of susceptible people, that is, people who aren't immune, and to the number of infected people. Right? That is, if there's more infected people, twice as many infected people leads to twice as high a chance of more people becoming infected. But also there's an influence of how many people could be infected. If you have half as many susceptible individuals, there's only half as much chance that people half as many people will become newly infected. This is actually one of the key ideas underlying the concept of so-called herd immunity to diseases. For people who recover, that's going to be proportional only to the number of people infected. If there's more people infected, more people will be recovering simply because of kind of the laws of sort of mass action. This is the parameters of the disease. This is how the disease is sort of transmitted in an approximate sense. Now we have our questions. Imagine that a couple returns to their town, population 100,000, after they've both been infected while on vacation. If the parameters of this sort of new infections and recovery are such that 5% of the infected individuals recover every day, and each infected person infects only 0.0002% of the susceptible population each day, how many people will have been infected in a month, in 2 months, in a year, so on? How do we answer these questions? How do we look at dynamics of disease propagation through a population in this? Once again, we're going to start this in a very systematic way. What are the variables in the problem? What are the here? They're the unknown parts of the problem. What are the things that we don't know? How many people are infected? How many people are susceptible? How many people are recovered at a given point in time? We'll define these as I for infected, S for susceptible, R for recovered. They depend on time, so we'll write them sort of with as functions of time here. The reason I'm choosing these, I is not a particularly late letter in the alphabet. It's not a usual choice for a variable name. I'm using these because these follow a very long established convention in the field. These models of mathematical modeling of infectious disease date to the early 20th century. And in those very early models, this notation of I, S, and R was established. And so I'm using that to stick with convention. Once we have our variables defined, we can think about writing down our problem. Right? What we're going to have is one equation for each type of person. Infected individuals, susceptible individuals, recovered individuals. And the equations are going to describe how the numbers change from one day to the next. This is not that different than the stochastic model that we just discussed about weather. Right? In that case, we had a counter variable I that said what day are we on, and the equation said what's the probability on day I plus 1 given the probabilities on day I. Here we're going to be looking at what are the numbers of individuals on day t plus 1 given the numbers on day t. Each of the equations is going to start with the number we already had and then have a term that says how did those change, one or more terms. We can, in a schematic sense, think about how can individuals sort of transition from one state to another. Susceptible individuals can become infected. Infected individuals can recover. This is the only path there is. An infected individual cannot become susceptible because infected people gain immunity. Recovered individuals cannot become susceptible because immunity is permanent. Recovered people cannot become infected because they are immune. Right? This type of model in the field of epidemiology is known as an SIR model because of this pathway. The equations that we write down from this are as follows. The number of susceptible individuals on the next day are the number of susceptible individuals that we started with minus how many individuals became infected. This alpha is 0.0002%. We have to add an extra 2 zeros for the percent. Multiplied by the number of susceptible individuals and the number of infected individuals. Each infected individual infects 0.0002% of the susceptible population. So this alpha times S tells what is 0.0002% of the susceptible population. And then we multiply that number of individuals by how many infected individuals they are to get the total number of new infections. Right? New infections decrease the susceptible population. Infected individuals, the number of infected individuals the next day is how many were currently infected, plus how many new infections there are, minus how many people recovered. Right? So some infected individuals recover, they're no longer infected. That recovery is represented by this beta times IT. The number of infected individuals, 5% of them recover each day, so beta is 0.05. 0.05 times the number of infected individuals is how many recovered. Alpha and beta are chosen here as the symbolic constants, again following fairly common standards in the field. Right? What's the change in the number of recovered individuals? Well, you can only recover after having been infected. So the number of recovered individuals the next day is how many were already recovered, plus how many were newly recovered. There's really only two numbers we're calculating here. How many new infections are there and how many recoveries are there? And these get added to the base numbers to find the numbers on the next day. This is our model, our set of equations that allows us to work with this system. What do we want to know? How many people have been infected in a month? How many in 2 years? How many a year from now? Right? Well, what does it mean to have been infected? The number of people who have been infected is the total of how many are currently infected, plus how many have been recovered. Depending on what you're interested in, you might want to know either one of these individually instead of the sum, but as posed, this is what we would like to know. And we would like to know this for t equals 30 a month from now, t equals 60 2 months from now, t equals 365 from now, a year from now. We know that the number of infected on day 0, the starting point is 2, that couple that returns to the population. Sorry, there's an inconsistency in here in terms of the total numbers. This is for a population of 1 million, not of 100,000. I'll update that on the slides that I post. And the number of initially recovered individuals is 0. In this kind of problem, the only thing we can really do is an iterative solution. That is, we solve for the numbers on the first day, then on the second day, the third day, and so on. If we want to find this for day 30, 60, 365, this is ridiculously tedious. Do not try to do this by hand. Nobody tries to do this by hand. The way we need to solve this kind of problem is with a computational solution where we let the computer go through all of these iterations. If you do that, what you find out with, and actually the error is only here, this should just be 99,998, because I have actually run these numbers with a population of 100,000. The computational solution gives you, after 30 days, there's 175 people have been infected with 20 new infections per day. A moderate number, but not a really scary number. After 60 days, 10,000 people, 10% of the population, have already been infected, and there's almost 1,000 new infections per day. 1% of the population is getting infected every day. Very, very high infection level rate. And by a year, actually, the disease has swept through almost the entire population. 98,000 people have been infected, and there's no new infections. So given these parameters, actually the course of an infection through a population leads to 98% of the people getting the illness. About 2,000 people don't, right? A little bit less than 2,000 people just never get it, because herd immunity kicks in for those last few people.